this reciprocal. So if we continue like that, so if we just continue like that, so what we would get is this kind of an expression. So x is so continuing. So we continue till we don't hit a 0, till xi does not become 0. Continuing. So continuing in this way, what we would get is x is, so let me write this, x is a naught plus xi naught. That's the way we started, a naught plus xi naught. Then this is equal to 1 over xi naught is equal to a1 dash, which is a1 plus xi1. Then writing becomes easy. So 1 over xi1, just write like this. So a2, so just this index increases by 1 here, and that remains, and this is xi2. So keep doing that. So keep doing that. In general, this is xi j, or say xi n, is equal to a to a n, sorry, a xi n minus 1, say the nth stage. It started from 0, so nth stage should be 1 over xi n minus 1, and so a n dash, which is a n plus xi n. So there you get xi n, and we stop. The algorithm terminates when xi n is equal to 0. And it gives the expansion, CF expansion, continued fraction expansion, which looks like this. So x is equal to a naught, a1 till an. So the an is the last entry. So this is what we get. So that's the algorithm. As you understand, it's quite easy to follow. And let me go to the next page. Now what we have to prove is that every rational number can be written as a finite continued fraction, and also the converse. Converse is actually easy. If you have a finite continued fraction, then it is certainly a rational number. So what is not completely obvious is the other direction, that every rational can be written as a finite continued fraction. So let's write that as a theorem. Any rational number can be represented. In fact, we also know some amount of uniqueness. If you do not allow the last entry to be 1, then it's unique. Rational number can be written as a simple finite simple finite continuous fraction. Let's see the algorithm for this, which is actually the just proof of this. So quite an algorithmic proof. So let's start with the rational number. So let's see a quick proof. So start with a rational number. Let x be h over k. H over k with k greater than 1. With k, the denominator greater than 1. So if the denominator is just 1, then we have an integer. So, and then we know it's just continued fraction has only one entry. So we start with the k which is greater than 1. Then just use Euclidean division to write h as a naught k plus, I just want to use the same notation so that it, yeah, so a naught k plus k1 and 0 less than equal to k1. K1 is strictly less than k. So this is just by Euclidean division. And then write, so we are essentially doing the same thing. So just for a back calculation, so we want to write h by k. So h by k is now a naught plus k1 by k. And what we do in continued fraction, we always invert this part, this fractional part. So this inverted one would be just k by k1. So that was the notation we were using. We'll use the same notation. So chi naught is, oh sorry, chi naught is k by k1. Sorry, chi naught is k1 by k. We were just writing a naught plus chi naught. It was just trying to use the same notation. Okay, yeah. Then we were inverting that. So chi naught is the fractional part here. So this is chi. This is chi. And so just write in exactly the same way. Okay, so if this is chi naught, then as we already wrote in the site, so if this is a naught plus chi naught, and then we say that a1 is 1 over chi naught, just as we did in the previous page. So this is k by k1, we invert it. And then use Euclidean algorithm again. So k is a1, k1. So k is bigger than k1. So this is greater than 1. So a1, k1 plus k2. a1, k1 with k2. And so using division algorithm, where this is 0 less than equal to k2 less than k1. And then write. So we are now going to define chi 1 and do the same thing. So chi 1 is now, so that's what makes notational, it's notationally easy now, k2 by k1. So if you just use consistent notation, it becomes easy to write. And if you, so what we have done so far is a naught k plus k1, this is k. Then k is, so we keep doing this, k1 plus k2, and k1 is k2 plus k3, and so on. It goes on like that. So how long we can do that? As long as this chi not chi is not 0. So this continues till chi n is not 0. And chi n is defined by this. So chi n is, so chi n is kn. Chi n is kn plus 1 by kn. So just using this same notation. And therefore equivalently, when, so we stop equivalently, we stop when kn plus 1. So in terms of kn plus 1 is 0. Yeah, okay. So till this is 0, sorry, till this is 0. When you reach 0, you stop. Let's write like this, that this continue till is a bit unspecific. So we just write that we stop when this is 0. And so the purpose of writing it in this way is that we wanted to just have correspondence with the Euclidean algorithm. So in terms of Euclidean algorithm, this stops when kn plus 1 is 0. So therefore, the previous one is a complete division. So you get an integer. So you don't have a remainder. So these ki's are all remainders at various stages. So you don't have this at that point. Yeah. Now, the point is, why should this happen? Why should this happen? Why will it stop at all? So the point is that k1, or even start from k1, k2, etc. All these are strictly decreasing sequence. They are strictly decreasing. Decreasing sequence of integers, of positive integers. So since they are strictly decreasing, they have to become 0 at some point. Therefore, k of, say, some n plus 1 has to be 0 for some n. So now note that this process does not work for irrational numbers, because the Euclidean division, what we are using, doesn't work there. It's not a quotient of integers, so it's not going to work. So this we are starting with a rational number. That is why this works, this Euclidean division, and it's going to terminate at some finite stage, because all these remainders form a strictly decreasing sequence, and they are all positive integers, so they have to become 0 at some point. So, and if this becomes 0 here, then our xi n is 0. So that's the correspondence we have, that xi n is kn plus 1 by kn plus 1 by kn. So if kn plus 1 is 0, then xi n is 0. And we end up then this, and our continued fraction is a naught, a1 up to a capital N. So it stops there. Stops there. So this actually corresponds to the GCD algorithm. So we are just rewriting the same thing, very much the same thing. Yeah, I mean, if you note, then this kn, so kn plus 1 is 0, so kn is actually the GCD. That kn is actually the GCD of H and K. Just let me write it. Is that? So note that. Okay. Now what we want to prove is the difference between various convergence and the number. So we are still working with rational number. We're going to have a finite continued fraction. And what we want to look at is the difference between convergence and the number. So let's do that. I would use the another page. In fact, if you note that that pictorial algorithm that we do that we saw in the beginning is exactly the same thing as Euclidean division. So we have seen this on the very first day. So we use this this pictorial method of filling with squares the minimum number of squares, always choosing squares of the largest size to fill up a rectangle, and that gives us continued fraction expansion for rationals. For example, it is the 65 by 18 here, so we got an expansion. So we wrote down the expansion in this. So these are the convergence. So 3, 1. Sorry, these are the partial quotients, and convergence are these numbers that we add up. And so when we cut the partial, when we cut the continued fractions, so let me just go to the where we are about. Yeah. So we want to write now. We want to understand the difference between the number and its convergence. Between a rational, just start with rational, and its convergence. So we start with a finite continued fraction. Now we know that every rational can be written as a finite continued fraction. Let it be this. And what we want to write is, so just recall that this convergence convergence are this Pn by Qn, where P naught was A naught and P1 was A naught A1 plus 1. Correspondingly, Q naught was 1. Q1 was A naught. No, sorry, this is A1. Q1 was A1 and Pn is An Pn minus 1 plus Pn minus 2. Qn is equal to An. Similarly, Qn minus 1, Qn minus 2, and this works for all n greater than equal to 2. So this we have seen. And these are the convergence. So we want to look up the distance between the number and its convergence. And also remember that we have this notation of what is called this complete quotients. So just recall that. Okay, let's write it like this. So x also can be written as A naught, A1, say up to An minus 1, and then rest of it you can put it in put it as this An dash, and this An dash is obviously the continued fraction starting from A naught and up to this An. So this part you are just writing it as a single entry, and these are called nth convergence. So this is nth complete quotient. So this is nth. Sorry.
Hey, puppy. Put up on a
Participants, please mute yourself.
So this is nth complete quotient. And if we use that notation, then we can write x as An plus 1 dash Pn plus Pn minus 1. So these are this An plus 1 is N plus 1 its complete quotients. So N plus 1 dash Qn plus Qn minus 1. This we can do for 1 less than equal to n less than equal to n minus 1. Okay, so we would also suppose that let's do that. We would suppose that n is greater than 1, so at least 2. N is greater. So we can write like this, and then we look at the difference. So we look at x minus Pn by Qn. So x minus Pn by Qn, An plus 1. So use this expression for x. An plus 1 dash. So these are these complete quotients, and then sorry, this is Q. Qn plus Qn minus 1. And then you have Pn by Q. So we multiply, and so Qn into And this first one is an plus 1 dash qn plus qn minus 1. And if I multiply this by qn and this by then the first entry is it gets cancelled. So this is an plus 1 dash pn qn, and from this other side also you get minus of the same thing, an plus 1 dash pn qn. So that's cancelled. So only the other two survives. So what we get is, let's write P first. So Pn minus 1 Qn minus Pn Qn minus 1. Now recall that this is nothing but minus 1 to the n. We have seen it earlier. So this is the numerator is just that, and denominator what it is. Just let it be like this. An plus 1 dash qn plus qn minus 1. So now we write qn dash, just to make it a bit shorter. We use a notation for, this is just a notation for an plus 1 dash qn plus qn minus 1. Just use this notation. So that would give us x minus pn by qn is equal to minus 1 to the n divided by qn dash. Okay. No, I would just like to keep this notation with the proper. So this is n, write it like this. So this nth one is defined in the same way actually. So n minus 1, n minus 2. So this is n plus 1. So n plus 1, I think. So this is just a notation for this to make it a bit shorter. So we are not considering the case n equal to small n equal to 1, and so this is no, 1 is okay. Small n should not be 0, so that should be considered separately. So the other two cases, 0 and capital N, has to be considered separately. So I would put it in my notes, but I'm not doing it now, just to be a bit brief. So now what we want to do is to find a lower and upper bound for this number, for this qn dash. That will give us a bound for the difference. Oh, sorry. Yeah. So what we want to do now is, so this is what we want to do, to find upper and lower bound for upper and lower bound for qn plus 1 dash. So let's do that. So just yeah, let's do that. So lower bound first. Lower bound. So an plus 1 dash is equal to, sorry, so qn plus 1. We are trying to bound qn plus 1 dash, not qn plus 1 dash is equal to, just recalling the notation we just wrote, qn plus qn minus 1. That's what we do. So this qn is an dash, qn dash is an dash qn minus 1 plus into qn minus 1 plus qn minus 2. So if I'm putting n equal to, if I'm replacing n by n plus 1, then this is what I do. Now recall this. So this is very much important that this recall the relation between an and an dash. So an is less than an dash less than an plus 1. So we use this when we proved the uniqueness. So sorry, it's the other way around. So an is the integer part of an dash. That is how we are constructing it. So this is what it is. So we want to use that here. So an dash is, so we are looking for a lower bound. So this is an plus 1 qn. So if I'm replacing an dash by an, I get a lower bound in strict sense actually. And this is nothing but qn plus 1. This is exactly the definition of qn plus 1, denominator of the complement. So we are happy with that lower bound. So we'll take that as lower bound. Upper bound, let's write this again and essentially do the same thing. So an plus 1 dash qn plus qn minus 1, that's the definition, and then use the same inequality. So this is what we so we use the other side of it. So we get a strict bound an plus 1 into qn minus 1. So therefore this is an qn plus qn minus 1 plus qn. Just made a mistake. Yeah, I just made a mistake because this is for n. This is for n. I'm using it for an plus 1 dash. So this is also should be an plus 1. So this is this is an plus 1. So if I have an plus 1 dash, then it is less than an plus 1. So for n plus 1, it is n plus 1. Yeah, this is an plus 1, not n. So an plus 1 qn, then you have this qn minus 1. I brought it here to so that we get the formula for qn. So this is qn plus 1. Sorry, this is qn plus 1. This is exactly qn plus 1. Then you also have this qn. So this is qn plus 1 plus qn. And let's take a slightly larger bound. That will serve some good purpose actually. So if I just multiply this by an plus 1, which is as we have already always assumed that all partial quotients except for the first one are positive integers. Non-zero positive integers are natural numbers. So they are at least 1. So I'm multiplying by something which is at least 1. So we get an upper bound qn. And this is nothing but qn plus 2, the next iterate. So the next denominator in that iteration. So the denominator of the next convergent. So that's a lower bound and that's an upper bound. So we have these two bounds. So what will we get now by this? So let's just recall this. Let's give it a number. Let's call this. I don't know actually. I don't remember the numbering. So I'll correct it. So let me just say 5. Don't exactly remember. I'll correct it when I send them. So now let me just put 5. So 5. So just recall 5. So this is Pn by Qn. Sorry, I don't want to put it now, but then let's just recall what it was. By Qn into Qn. Yeah. So Qn and yeah, I just wanted to make sure about the power of n. This is Qn plus 1 dash. So Qn we would keep it as Qn and replace this Qn plus 1 dash by its upper and lower bound, which we just calculated. So if I just put the absolute value on both sides, the minus 1 power n part just becomes 1. So 1 by Qn plus 1 dash. Now let's use the upper and lower bound. So so it's a reciprocal. So upper bound becomes a lower bound and lower bound becomes upper bound. So 1 over this is just lower bound is Qn plus 1 and upper bound is Qn plus 2. Just write that. Therefore, what we get is 1 over Qn plus 2, which is strictly less than x minus Pn by Qn less than 1 over Qn plus 1. Now, if I multiply the entire inequality by Qn, then what we would get is Qn plus 2 is less than Qn x minus Pn is less than 1 over Qn plus 1. So let me call this 6 and this as, yeah, let's just call it 6. So then what we have got are two important things. First of all, x minus Pn by Qn, this is what we wanted to estimate, how close the convergence are. So we saw that this is 1 over Qn plus 1. And therefore, since the denominator of the convergence are increasing sequence that we have seen earlier, this is going to be less than equal to 1 over Qn square. So this is because Qn plus 1 is strictly greater than Qn. So these are strictly increasing sequences. So which is obvious from the definition, in fact, from the iteration. So this is what we got. So this gives us the degree of approximation by convergence. So obviously, as you take a larger n, so as n becomes larger, you get better and better approximations. And let me, and the other thing is also very important. That's why we have both these bound. So that has a nice thing to say. Let me just go to the preview. Go to the next page. Just copy this. So let's analyze this inequality. So this is just what we got. So it's quite a significant one. So what it gives is this kind of a thing, that if you start with say somewhere like Qn, then you have less than Qn minus n minus. So I'm replacing n by n minus 2. So this is Pn minus 2. This is less than 1 over P. Sorry, this is Q. Q n plus, no, sorry. This is Qn minus 1. It should be 1 less. And this is less than, by using the same thing, n minus, okay, actually I should probably just start with this. Let's just make it, otherwise we're writing too many n minus 2, n minus 3, etc. So let's start with this itself. So this is what we have proved. Now we are trying to see a consequence. So Qnx minus Pn, Qn plus 1. And now if I simply iterate this with n replaced by n minus 1, then this is what you get. So if you replace n by n minus 1, then the lower bound is 1 over Qn plus 1, which is exactly what we have here. So this is Qn minus 1 x Pn minus 1 less than 1 over Qn. So n is now replaced by n minus 1. So this is exactly what you get. So therefore, this Qn into x minus Pn, this quantity decreases in absolute value. Let's put the absolute value, otherwise it actually changes sign. So this decreases as n becomes bigger. So as you can see from here, that this the same expression for n minus 1 is strictly larger than this. Decreases strictly with n. Okay. So we are done actually with the approximation. We can prove some kind of some more things. For example, an important question and very relevant question would be to ask whether this is optimal, whether this estimation that we proved, whether it is optimal. So we'll see those later. Now let's just be happy with what this approximation we got. So I have like 20 minutes. Let me try to. So we actually have to look at this infinite continued fraction. Much of the theory will carry over. Maybe because I have a 1 week gap, so it's probably better if I start with infinite continued fraction next week because of this gap. And right now, let's do something else. Let's see how these fractions, continued fractions, appear in various things that we see around us. Okay, let me start with an example. If I have time, then I'll try another. I have a shorter example and a longer example. Let's start with the longer one. Yeah. So that's like essentially, and aside from the theory, so okay. So let's start with this question. You must be using this A4 size papers. So A4. So maybe we should just title it as use of continued fraction. Use of okay, let me see how much space I have in this page. Okay, that's quite enough. So use of continued fraction. There are many actually, lots of use. And in many ways, actually, continued fraction turns out to be the best way to write an irrational in particular. So it shows patterns. Anyway, so we would see some examples in that way. Let's start with so A4 size paper. So what is A4 size paper? So A4 size paper, meaning what are its dimension? Meaning what are its dimension? So this is 297 millimeter cross 210 millimeter. So this is a dimension. So you might ask that it's a very strange number. So why should we consider a paper with this dimension? What's the advantage? So I mean, we could have just had 300 millimeter by 200 millimeter. That sounds much more logical. Then why should we have such strange measurements? So so how the papers are measured? So to do that, let me show you it. I'll just get a picture. Just one second. I have to get a picture. Oh, it's just become very big. Scale it. One second. I think it's quite nice. Yeah, it's perfect. I think it's perfect. Let's give it like this. So this is a picture of paper size. Let me just try to explain what I mean by this. 1 second. Yeah. So the largest size is actually A0. So its paper size starts with A0. So what is A0? So A0 is 1 square meter. 1 square meter. That's how we start. So that's the largest one. Then we cut it up. But how we cut it up? So the idea is to cut it up in such a way. Actually, I should actually draw it. Otherwise, it's difficult to. Let me draw a rectangle as well. Let me just draw this. So suppose this is the biggest one. So we have a rectangle. So all these papers are rectangular. Yeah. And the idea is that we are going to cut it into half. But when we cut it into half, the ratio of the sides should remain the same. So what we want is this, that cut into half along the say the length, the longer side, along the they call it along the cut into half along the length. Okay. So this is what we are going to do, and what we want is that the ratio of sides should remain same. Let's try to write it down mathematically. So if I say that the largest rectangle, the larger one is 1 and x. So 1 is to x. 1 is to x. Let me just write that. So this is x. So that's just a proportion. So we can write it like this. So 1 is to x. I mean, one of the thing like we can always say 1. So 1 is to x. X can be, of course, a rational number, not be an integer. So 1 is to x. And then we cut it into half along these sides. We get two rectangles, and this is now x by 2. So x by 2. Now the longer side is 1 and shorter side is x by 2. So what happens to the ratio? Just remember this. So length is to the breadth length is to the breadth so length was x, so x is to 1. That was the initial, that's what we started with. And then what we got is the following, that now the longer side, the length is 1 and breadth is x by 2. So this is 1 and x by 2. So x by 2 is the width. So length is x and width is 1. So x is to 1. Now length is 1 and width is x by 2. So we want these two ratios should be the same. What do we get from it? So we get that x by 1 should be equal to 1 by x by 2. Therefore, x is equal to 2 by x, which means x is square root of, we want a positive, of course, now we won't take minus square root of 2. So it's just a positive square root of 2. So square root of 2 should be the ratio of the sides. If we start with this ratio, if we start with a paper which is 1 is to square root of 2 ratio, then when we cut it into half, the ratio remains the same. the ratio remains the same, and this is what we yeah. So this shows this thing. So what should be the dimension of the largest paper? That also we should find it out. One second. So that's the rationale behind the A naught. So A naught has area of 1 square meter, and ratio of the sides and this is what we want, this square root of 2. So if you calculate, then what you would get is the dimension. So paper size. So A naught paper size is just let me, I have calculated it already. So let me just write this down. So this is 118.9 centimeter cross 84.1 centimeter. And then what is A1 paper? A1 paper. So what is A1? A1 is just cutting the longer side into half. So this the whatever was the width now becomes the length. So 84.1 centimeter into half of this quantity. So this is going to be approximately 59.5. So it goes on like that. And let me write up to A2. Okay, there's quite a few. So A2 is just similarly. So I just leave this and write about A4. A4 is especially nice and we use it often. So we get 29.7 centimeter into 21.1 centimeter. So now the point is that if you look at this ratio, this is an irrational number. So it's a never-ending decimal. So you need an approximation. And that is what we use when we write down these paper sizes. So let's just write down the continued fraction for, we want rational approximation. So what we want, we need rational approximation for square root of 2. And the easy way to get a rational approximation, which we have just seen, is by looking at the convergence of its continued fraction. So let's write down the continued fraction expansion first. So square root of 2 is greater than 1. So it should start with 1. 1 by, so 1 minus, so we have seen this method actually. So here Euclidean algorithm is not going to work because it's not a rational number. So it's an irrational number. We have seen this way of working in the first lecture. So this is, just write it like this. Just take the 1 out. 1 is the integer part of square root of 2 because square root of 2 lies between 1 and 1 and 2. Yeah, so therefore just write this as 1 by square root of, this is 1 by square root of 2 plus 1, or I would write it as 1 plus square root of 1 plus square root of. This is obvious because square root of 2 minus 1 into square root of 2 plus 1 is just 1. So they are reciprocal, the conjugates are reciprocal. So it's quite easy. And what we get is 1 plus 1 over 1 plus square root of 2. This is very easy. But then just note that this is all we need. Because this now we can repeat. Because square root of 2 is 1 plus 1 over 1 plus square root of 2. And then the square root of 2 we can replace by this all over again. And we keep doing that. So what we get is 1 plus 1 over. So this is going to become 2 because there isn't 1 here. So that will get added. So 2 plus 1 over 2 plus 1 over, and it will just go on like this. It just goes like that. So what we get is 1 comma 2 comma 2 comma, so that goes on till infinity. So that's infinitely many 1 followed by infinitely many 2. That's the continued fraction expansion for square root of 2. Now we need to have a suitable convergent. In fact, it turns out that this seems good enough. So this one, I guess this is 5 2's. So if you just take this, just truncate it at this point. If you just truncate it at that point, so you are starting with 1 and then considering just this 5 2's. So this is a convergent. So whenever you cut a continued fraction, what you get is a convergent. This is what we have been writing as Pn by Qn, and this is yeah. So if you calculate, this turns out to be 1 second. Nine by 30. Yeah, so this this turns out to be actually yeah. So this is 99 by 70. 99 by 70, and just multiply by 3 up and down, then you get 297 by 210. It's same as this. So this is a convergent. So 297 by 210 is a convergent of square root of 2. So it approximates square root of 2. And this is exactly the proportion of an A4 size paper. So A4 size, the dimension of the A4 size paper is exactly a convergent of the continued fraction of square root of 2. And the logic behind the square root of 2 is what I explained at the beginning, that you have a rectangular paper and what you want to do is cut it into half. And every time you do that, you maintain the same ratio of length and width. That is so, and that just gives you immediately, that gives you this ratio, that it has to be square root of 2. But square root of 2 being an irrational number, you have to you need a rational approximation to make it workable, and we'll do it via continued fraction. And this is exactly the one that is used. So 297 by 210. It's exactly the the ratio of the exactly gives the dimension of this A4 size paper. So that's one of the use. Yeah, okay. My time is up. So we'll see more examples later. I wanted to show you something. So do you have any questions? So if you have a question, then you can ask, because I want to stop share and then share something else. So if there is anything you want to ask, please do so. I actually want to show you a web page. Yeah. Okay. So I assume that there's nothing to ask. So I would just I would stop share and then share again, say something else.
Okay, sir. Okay, sir.
So I'll just take 2 minutes. I know it's just 2 minutes. Stop sharing. Yeah. Then let me share something. Oh, there is some chat message. Oh, that's just no doubt. Okay, thank you. Anyway, if you have doubt, it's even better. Share. Yeah. So what I want to share is an online calculator of continued fractions. So there is a website. So can you see that?
Yes, sir.
Yes, sir. Yes.
So this is a website which has calculators, continued fraction calculator. So I'm going to send you the link as well. So let me just show you an example. So it has various nice things. So this gives you Euclidean algorithm actually. So it gives everything. Quadratics, square roots. 1 second. This is fraction. This is for rationals. Yeah, I can even in fact show you this. That this is how it works. So here you can just put the continued fraction we talked about. So 2 comma, so 1 comma 2. So the here the notation is slightly different. First entry is followed by first entry, which is the integral part, is followed by a semicolon, not just a comma, and later on all commas. So we have these 5 2's. 5, I think, yeah, we have 5 2. So if I this, then this is 99 by 70. So that's 99 by 70. That's what we were saying. That if you multiply numerator and denominator by 3, then what you get is this 297 by 210. So that is one thing. One second, not expression. Square roots. Yeah, square roots. But square root probably won't work here. Let me try. Maybe it will take it 0. No, it doesn't work. It doesn't allow 0 in the first place. But they have other calculators. Okay. No. Okay, so it has various calculators. Yeah, so square root of 2, I don't know how to calculate. Yeah, it's only so so it has a quadratic square root calculator, but you can't put 0 as the first entry. You have to put an integer. Yeah, they have to be all integers. So 0 is not allowed. So we can't really calculate square root of 2, but square root of 2 is anyway trivial. Yeah. So okay. So I'll share the link to this web page. You can try calculating continued fraction, and this web page also has a lot of information. Okay, so stop sharing this. So I think my next lecture is next Tuesday. So I will
Yes, sir.
start with the infinite continuous fraction. Thank you for attending.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.